Hello, everyone. I hope you can see the screen and hear me well. Okay. So welcome to our presentation. I'm Chao Li, and research associate in the chair of architectural informatics, Technical University of Munich. Recent years, there have been many practices for additive manufacturing in construction. For instance, the high-res slab produced by ETH2 claims that it saves approximately 70% of material compared to the conventional casting method. The mesh company is able to manufacture free-form reinforcement structure with robotic arms. The first 3D printed residential building in Germany was finished in last summer. And the wall panels with the textile reinforcements has also been prefabricated and then assembled on site. The TRR277 project funded by German Research Foundation is dedicated to explore the EM technologies in construction from three perspectives, namely the material and processes, computational modeling and process control, and then the design and construction. However, when we are talking to the additive manufacturing in architectural design, challenges do exist. The complicated EM knowledge includes the processes by their own and the machine system, the regulations and the function optimizations, etc. During the early stages, the knowledge of AM are usually not well informed, but the decisions need to be made for suitable manufacturing methods. And how can we support the architects? As you know, the logic-based knowledge representation has been recognized as a symbolic top-down manner in the paradigm of artificial intelligence. Using the semantic web technology stack, the knowledge can be formalized with the web ontology language of all accessed through the query language of Sparkle. It is also possible to exchange different rules using the unified rule exchange format. Our research goal is to establish a design decision support system based on the formal knowledge in the BIM environment to assist the architects and engineers to choose suitable AM methods. In order to achieve that, we formalized the explicit knowledge of additive manufacturing in forms of ontologies and rules, such that the architects and engineers are informed of the capabilities and limitations of AM methods, and timely design adaptations are enabled. Afterwards, the decisions of appropriate AM methods are supported by the upcoming multi-criteria decision-making methods. Development of the ontology follows the workflow of specification, knowledge acquisition, formalization, conceptualization, and validation. As to specification, a set of competence questions are asked to clarify the scope and function of the ontology. Activities in the knowledge formalization are reviewing the bibliography and conducting semi-structured interviews, and the AMC processes, parameters, boundary conditions, etc. Are then conceptualized in the conceptualization step. Afterwards, the formalization step encodes the concepts and relations using the OR language. The rest competence questions in the specification step are then answered during validation. Up to now, we formalized several modular ontologies and imported them to build the AMC knowledge base. Basically, the parameters describe the properties of the materials and machine systems, which are further imported into the building components and AMC methods. Here we have the brief view of the taxonomy of the knowledge base. We can see that the AMC processes, the materials, and the boundary conditions, functions, etc., are embodied in this ontology. relations are created to link the building components properties to the AM methods. The metrics for this ontology present that we have a number of classes and properties. On top of the knowledge base, the rules can be applied to detect the manufacturability of building components, mainly by comparing the processes, boundary conditions with detected features from the design. For instance, if the manufacturing feature exceeds the limits of one AM method, we assert that such a building component is not manufacturable by this method. Similarly, other rules, including the logistics and the construction plan, can also apply. Here's the workflow of assessing the building components manufacturability. In the BIM environment, extraction of semantic information is relatively straightforward, but the geometric features such as overhangs, minimum volume, bounding boxes, curvatures, etc., requires the tailored algorithms. Until now, we kind of approximated the overhangs and calculate the vertical minimum volume bounding boxes. Afterwards, the detected features as well as the semantic information are stated in the local replica of the knowledge base. Inferences are enabled by embedded reasoner compatible with all and SWOR rules. And in the end, the feedbacks are visualized in the BIM output tool. The illustrated technology framework presents the four major components, namely they are the AMC knowledge base, the toolkits on the BIM outline tool, remote procedural core, and the portal of the design decision support system, where the palette reasoner is embedded for inference capabilities. Accordingly, we established a prototype. The architects can select a building component, and then the system extracts the manufacturing feature and the semantics, presenting them on the design decision support portal. Afterwards, the architects evaluates the building components material, building spaces, and geometric conformities regarding to individual AMC methods. Applicability is then informed, and architects can visualize it back in the BIM outline tool. So here's the video. A first communication channel is established, and the features are extracted, computed, and the architects can select the AM methods for evaluation. And then they will be informed of the conformities and visualize it back in the BIM output. Yes. In the future work, we would like to enhance the ontology, basically by introducing the upper ontologies and align our ontology to an IFCO, which is the ontological version of the IFC data schema. Also, we would like to extend the functionalities by enabling the automatic workspace generation from the ontology. And we want to detect more features and present them for the better support. Okay, so this is all for my presentation. Thank you.